Okay. So we're passing back the quiz. So I think you guys did okay. The average is 80%, which is pretty in the ballpark of what we had in the past around this time. A little better than last year, so this is good. We have quite a few A's. Those of you that did not do well, it's okay. It's not the end of the world. The quiz is out of 30, which is equivalent to one full lab report. So if you do well on lab reports, you kind of even out your grade. And if you have questions, let me know. I posted the key online, guys. Oh, your energy is so great, but just keep it quiet a little bit. I put the key online, so you can look at the key and let me know if you have any questions there. All right. Picking up where we left off. What are the advantages of HPLC over low pressure liquid chromatography? Do not look through your notes, just what you remember and what is logical.
Better resolution?
Raise your hand. Okay, Sam.
Better resolution?
Better resolution. What else? Yeah?
Faster.
Yeah. So it's faster and better resolution. That's the main thing. And better sample recovery in terms of purity. Okay. What is gradient elution in HPLC? Amanda? Changing the concentration of the mobile phase over time. And that is basically trying to increase the strength of the mobile phase to compete with the stationary phase to help with reducing the analysis time. Okay. What is guard column and what is its function? Laura?
So it goes before the actual column, and the same thing that's in there is the same as the stationary phase, and so it gets an impurity before they actually get into the column.
Exactly. So it's guarding the column. It has the same stationary phase, same material that is in your actual column, and acts kind of like a filter that traps all impurities from getting onto your column that might block your functional groups, so that you extend the life and the efficiency of your column. Eventually, the guard column will die out or get maxed out in capacity, so you would change it more regularly than you would change your column. How many solvents and pumps can one use in HPLC, or can an HPLC have? Michelle? A maximum of 4. So you can have a quaternary system, you can have tertiary system, binary system, or one pump, one mobile phase, one solvent. How does the packing and thickness of the stationary phase impact resolution? Jason? The better packed in terms of under pressure. Okay, so you would have less, what we call it, vacuum, not vacuum, a void. Less space, less void, better resolution. What about the thickness of the stationary phase? If it is thinner, if it is a capillary with a very thin stationary phase, and then better resolution. Yes, do you know why?
There's less space to interact.
Yeah, less space, less amount of stationary phase that the sample can diffuse in, so you reach equilibrium faster between stationary phase and mobile phase, so you have nice sharp peak. The only drawback is that if it's just a thin layer of stationary phase, the drawback would be the capacity of the pump. That means you cannot load a lot of samples. It's very easy to overload the sample or overload the column. So it doesn't handle high concentration. Okay, what are the advantages of a narrow diameter column? So narrow diameter, it's kind of related to the amount of stationary phase that you have. So with narrow diameter column and longer column, you basically have better resolution, sharper peak, higher sensitivity, and lower threshold. So you get really nice high peak and also very, very sharp. So it enhances the sensitivity of your detection. What's the difference between a PDA, a photodiode array detector, and a variable wavelength detector? You all had the labs already, okay? Tia? Yeah. Exactly. So the PDA gives you a scan of wavelength, a scan of absorption over a range of wavelength, whereas the variable wavelength detector measures absorption at a selected wavelength, a maximum of 2 wavelengths that you can select. So one gives you a better or more identification power because of that fingerprint that it gives you. The other one, it's mostly for routine work. Once you know what your lambda max is, then you would select the wavelength and be used mostly for quantification of the routine type of work. Okay, this is a very important table in a sense that it summarizes examples of what different compounds or analytes you can detect or analyze. These are just examples. What separation modes you would use, and what's the detection method. So oftentimes in an exam, I tell you, okay, here's the looking at a particular component. Give me a chromatographic type. So you're going to say HPLC or GC. Let's say you said HPLC. I'm going to ask you for separation mode. You're going to tell me normal phase, reverse phase, cation, anion exchange, or affinity chromatography. You're going to select a separation mode, and then I'm going to ask you, what's the detection? How are you detecting your compound? So you're going to say the type of detector, electrochemical detector, or it's going to be a fluorescence or an UV absorption detector or a UV vis absorption detector, mass spectrometry, post-column analysis. So you're going to tell me how you detected it, how you separated it, how you detected it. So there's 2 components to the question. So this is a good summary table for you to study from. So very briefly talking about applications of high-performance liquid chromatography. There's numerous applications, and throughout the semester, we're going to talk about a lot of these applications. So when we talk about carbohydrates, for example, we're going to talk about how we're using normal phase for sugar analysis. So I'm going to give you a lot of details there. When we talk about pesticides and vitamins, I'm going to show you how normal phase can be used. So a lot of chapters later on is going to be based on HPLC detection, GC detection. So now we are learning the techniques, and most of the chapters later on we're going to learn the application. So chromatography is going to stay with us till the end of the semester. So that's why the final is cumulative, because you need to learn chromatography and you need to keep that knowledge till the end. So we'll learn about these applications, like I said, later, but mostly in normal phase, we're trying to separate relatively hydrophilic compounds. One thing you really want to remember and not forget about chromatography is the first step is interaction with the stationary phase. If you do not have an interaction, you do not have separation. Really, you need to get that concept. So if we have normal phase, that means your column is polar. So your interactions are based on polar interactions or hydrophilic interactions. So you need to get that concept. If you have reversed phase, it is a nonpolar column. So your interaction is based on nonpolar interaction. So mostly hydrophobic species. So we're going to be using reverse phase for different applications. For example, amino acid separation and protein separation, peptide separation can be done by reverse phase chromatography. Alkaloids such as caffeine, some fat-soluble vitamins, phenolic compounds, some mycotoxins and antibiotics, some pesticides. I say some because some pesticides are polar, others are non-polar. So it really depends on the chemical structure of the pesticide, of the mycotoxins, of the antibiotics. There's so many, there's a big group of chemicals that differ in their characteristics. I have ion pair reverse phase here. What's that mean is my stationary phase is nonpolar. And I'm trying to separate compounds that have charge. So they do have some hydrophobic components of it, but they have charge too. To enhance interaction with the column, I put ion pair in it. That means I put some ion species in my sample and mobile phase to block the charge on the compounds so that they can interact better with the nonpolar stationary phase. And that's why we call it ion pair. So we're pairing the charges with an ion that blocks these charges on the molecule so that it can interact via hydrophobic interactions or nonpolar interactions. This is just illustration of a chromatogram for normal phase separation of rice bran component versus reverse phase separation of vitamin B6 components. It's just an illustration of chromatogram. There's nothing there other than that. With ion exchange, we're separating molecules that carry charge, amino acids, proteins. We can make carbohydrates carry charge if we change the pH or if we pair them with an ion. We're going to learn about that when we cover carbohydrate chapter. Inorganic anion, cations, organic acid, amines, phenols, surfactants, sugar, methionine. So anything that can be ionized and carry charge can be separated by ion exchange. Size exclusion is often use size exclusion with low pressure chromatography to separate and purify based on size, but high performance liquid chromatography can also be used with size exclusion, and it's mostly done to determine changes in molecular weight. So we can get rapid determination of molecular weight of proteins, starches, fiber components, and derivatives. Last, affinity. We can use affinity, especially in the determination on separation of glycoproteins, allergens, enzymes, mycotoxins. So we can use affinity chromatography for high level of purification. These are just examples of chromatograms using different modes of separation. Again, here's anions in coffee, the different components in anions. All that means that are negatively charged, and we're separating them. And here we're separating based on size. We can see the peaks here are not very sharp. This is taken from a low pressure liquid chromatography. But when we have high performance liquid chromatography, even though it's size exclusion, we get better peak and sharper peaks. So let's do an exercise for a +2. Take out a piece of paper and write your name on it. All I said is take out a piece of paper with your name. It's an opportunity to chat.
We need to talk about the piece of paper.
You need to talk about the piece of paper.
Yeah, we'll have to.
You guys. Okay. All right. Everybody, piece of paper, ready to go? Okay. So let me explain a little bit what you're looking at, and then you answer the questions of the next slide. So all of you have the HPLC lab now? Yes, congratulations. So I pulled up an isoflavone chromatogram for you and talked about it a little bit in anticipation of the liquid chromatography mass spectrometry lab next week. And then I only said it's a reverse phase. liquid chromatography. And I showed you that we have about 11 to 12 different isoflavones extracted from soil. But I didn't tell you about the method or the gradient. So the gradient starts at 17% acetonitrile. That means I have 83% water and 17% acetonitrile. So here, from 0 to 25 minutes, I'm increasing the acetonitrile concentration from 17 to 25. I'm leaving it constant at 25% for 5 minutes. Then I'm increasing the concentration over 10 minutes to 30%, leaving it constant for 10 minutes at 30%, then decreasing it back to 17%, and leaving it there for the last 5 minutes to kind of equilibrate back. Okay? So, and that's the separation I get. Very nice separation, sharp peaks, great. All right, so is this normal phase or reverse phase, and tell me why? I probably told you already what it is, but what is it and why? Why do you think it is what it is? Okay, someone's gonna raise their hand, or I'm gonna call on people randomly. Sammy?
It's reverse phase because you're increasing the non-polarity over time.
Thank you very much. Exactly. So it's a reverse phase because you see from my gradient, I'm increasing the concentration of acetonitrile, which is the organic phase, which is the less polar. If the water concentration was increasing, then you go, oh, okay, this is normal phase. I'm increasing the polarity over time. But no, I'm increasing the solvent, organic solvent over time. So I'm starting with a non-polar stationary phase and a polar mobile phase. And that's why it's reverse phase chromatography. Very good. Now, which of these isoflavones is the most polar? Do you know, Alice? It's the first one. So it is reverse phase chromatography. That means my stationary phase is non-polar. That means the compound that comes out first is the compound that's going to interact the least with the column. Right? So the most polar will come out first. Okay? And then the least polar is the last one. You don't have to read. It took me a while to be able to say them correctly. Okay. Now this requires you to think a little bit. How would you change the mobile phase so that genistein, which is the one that comes at the very end, would elute sooner, that means comes out sooner, without changing the relative positions of the other compounds? So what I'm asking you here to do, how would you change this gradient, this method here, so that this comes out sooner without changing anything here? So you're building a method, right? Think yourself, you're the analyst in the lab. And this is taking 60 minutes. I want to shorten my analysis time. Okay?
So it's like the gradient stops going up at about 40 minutes,
Yeah.
which is after aging.
Yes.
So you just keep increasing it instead of having a plateau right there.
Thank you, David. That is excellent. All right. So since everything comes out before my 40 minutes, so instead of just reaching 30 here, I can keep going after 40 minutes instead of keeping it at 30%. I can, let's say 40%, go up to 40%. Then this would come out sooner. And then my analysis time will be cut by 10 or 15 minutes. All right? Good. What would happen if you keep an isocratic elution mode at 17%? That means you didn't increase your acetonitrile concentration over time. You started with 17% and you kept it at 17%. What happens? Sam? Me? Sam? Aha. So my retention time is going to be much longer. So compounds are going to take, some of these will come out, and then the rest, they're going to be slowed down, and there is a chance that genistein will stick on the column and not leave, even though maybe it will leave after 24 hours, who knows. But it's just going to stay longer. And another thing you'll notice, like in the video that I showed you on Monday, the peaks are going to be broadened with time. So they're going to be more diffusion within the column rather than going in and out and equilibrium between the stationary phase and the mobile phase. They're not liking the mobile phase as much, so they're going to diffuse down the column and then the peaks will broaden. Then as we go down, you'll see that the peaks are going to be broadened, and when they broaden, we might risk that these peaks, instead of being sharp and nicely separated, might not separate very well from each other. Okay, one last one. What would happen if you keep an isocratic elution at 30% acetonitrile? So that means I'm starting at 30%. Instead of starting at 17, I'm starting at 30 and keeping it 30 the whole time. What would happen?
They will all be faster, and it might not be, I don't know, maybe some correlation that happens.
Exactly, not maybe, for sure. They will come out super fast. These two might not separate at all. They're very close from each other. They're polar, relatively polar. So they are not going to come out separated. These might co-elute, and these three and these three. So we are going to lose on sensitivity or selectivity of the column. So you will lose on selectivity, and then because you lose on selectivity, they will just leave with the mobile phase sooner than you want them to and not separate efficiently. Of course, your retention time will be shorter, your analysis time will be shorter, but you lose on resolution. Great. These are all things we think about when we develop our method of separation. Oftentimes, as a scientist, later on maybe in life, you become a scientist in a lab and you want to develop your own methodology. These are the things you want to think about. You have a complex mixture, you want to enhance separation, so you start thinking how you're going to build your program to get separation or to shorten your analysis time or whatever you want to do. So you have to think about method development, and this is just an example of that. Okay. So sometimes we use HPLC in tandem. That means we do separation using one mode of separation, but it doesn't give me pure compounds. I still have coelution of multiple compounds that are related. So to enhance the separation, I use another form of HPLC in tandem. That means the first one and the second one and then the third one. Here's an example where we use HPLC in tandem. So here's an example where I want to separate bioactive peptides. So what are bioactive peptides? You get a protein and you break it down by enzyme, and then you generate smaller chunks of the protein, smaller segments of the proteins. These segments can be bioactive. That means either antioxidant or antihypertensive, and you want to determine which one of these peptides is the most potent, so you can produce a supplement later on of that peptide. So you want to identify the peptide that has the highest activity. So in order to do that, you want it to be in its highest purity so that you can actually sequence it and identify it and then say, okay, I'm going to make a supplement out of this peptide and singular peptide. So what you start off with simply is when you produce a hydrolysate, that you have different sizes, and you know that your peptide is going to be small. It can be probably anywhere between, let's say, 1 kilodalton to 2 kilodalton, or even less than that. So you want to eliminate anything above 3 kilodalton, anything that is large, because peptides that are active are really small. So you use ultrafiltration, which is not the chromatography, just you're filtering out all of your large peptides, and you're leaving their extract with the small peptides. Then you can do liquid chromatography, ion exchange followed by size exclusion, or you can do size exclusion followed by ion exchange. Doesn't matter, the order doesn't matter. So you can separate based on charge, but multiple peptides can have the same exact charge. So they will come out as one peak. So let's look at that. So here, let's say you separated by ion exchange, and you took each fraction, you collected each fraction, and then you measured the activity. So here's an assay to measure the activity, and you found that fraction F has the highest activity. Okay, so your peptide is there. Peptide of the most potent is there. So you take that fraction and you go, okay, it's not yet pure. I do size exclusion. So now I'm separating this one fraction based on size. So now I separated based on charge and then based on size, and I ran my assay and I found that this fraction here, the fourth fraction, has the highest activity. But still, in it, it's not pure. I might have the same size, the same charge, but different polarity or relative polarity. So I can do reverse phase chromatography and separate based on their polarity, and then again look at the highest activity. And from there, take that fraction and finally do an LC-MS and identify the molecular weight and sequence of my fraction. So I can do sequencing, I can get the molecular weight, and then I can determine which peptide is the most potent. So it had to take 3 different chromatography and then a mass spectrometry analysis in order to get that last piece of information. So yeah, in many applications, one HPLC separation or one mode of separation might not be enough. You have to continue your analysis to get a purified component. Okay. So this is for the lab, but not yet. I'll show that on Friday, so don't worry about it right now. So I'll move to, I have 15 minutes to start a very interesting topic. Who likes physics? Oh no. Oh, you raised your hand. You like physics? Okay. All right, so let me narrow it down. Who likes optics subject in physics? Oh, come on. Life is fun, right? It's fun and different. What?
Waves and stuff.
Yes, waves and stuff. We're going to talk about waves and stuff. All right, Alex, what are you eating? Sharing is caring. Okay. Let's talk about waves and stuff. What do we know and what do we remember? What do we know and what do we remember? Hayden remembers something.
I'm going to go with C.
Hayden went with C. Anybody else either support Hayden or say you're wrong, Hayden? You're thinking A. Think about it a little bit more. Yeah,
I think it could be all of the above.
I agree with them. It is all of the above. So electric field and magnetic field are both associated with the wave and stuff. And photons of light are pockets of energy within the wave of light, or the electromagnetic wave. Light is an electromagnetic wave. So there is the electric field and the magnetic field, and the photons are particulate or pockets of energy within that wave of light. So yes, all of them are associated with the light wave. We're going to use spectroscopy. You already used spectroscopy in HPLC. Already looked at absorption. So spectroscopy is involved in so many areas in food analysis. So many different methods involve spectroscopy. So following spectroscopy as means of analysis, detection can be based on absorption of a photon of light, emission of a photon of light, or dissipation of heat. What's the most obvious out of the three? You already did that, Hayden.
I'm calling it me. I was going to say A and
You
C.
raised your hand.
I was going to say A and C.
Huh.
I'm wrong.
I didn't put it that way. You're partially correct. To be positive. So we definitely measure absorption. In some cases, we measured absorption down.
I think this could be all of the above again.
I'm not going to agree with you this time then. Ooh. Anna? A and B. So absorption, fluorescence. So we measure absorption of light. We measure emission of light. And the emission of light, we're measuring the fluorescence. So when we say a compound fluoresced, that means it emitted a photon of light or emitted light. So we're measuring absorption, we're measuring emission. Dissipation of heat happens because when you go from ground state to excited state, and then you go from excited state to ground state because it doesn't stay in the excited state after absorption of light, there is some dissipation of heat. Okay? Sometimes it's only dissipation of heat, sometimes it's a mixture of emission of light and dissipation of heat. But the dissipation of heat is so minute, the heat is so minute you cannot measure it. It's not measurable. So although it happens after the molecule or what have you absorbed light, it will go back to the ground state and it will dissipate heat, but it's not measurable. So when we are determining the presence or trying to detect a compound, we use something that is measurable, either absorption or emission. Okay. So if I want to define spectroscopy in simple terms, I would say it's the interaction of electromagnetic radiation, in other words light, with matter. So this sums up spectroscopy, interaction between electromagnetic radiation and matter. The matter is the species. So what kind of species do I have? Is it a molecule? Is it an atom? And if it's a molecule, what kind of a molecule? What atoms make up the molecule? What structure do we have? Do we have aromatic structure or we don't have aromatic structure? So the species dictates how the interaction is going to occur. Is it going to absorb light, and at what region is going to absorb light? So here what we see is there is an interaction, there is the species, there is the region. At which region it's going to absorb light or interact with it. So let's look at the interaction. So species matter, based whether it's atomic, whether it's the molecule, and also within the molecule, depending on the structure of the molecule, it will absorb at different wavelengths. Okay, the interaction can be absorption and emission. It has to absorb before it emits. It won't emit light if it doesn't absorb it first, but not every molecule can emit light. So not every molecule or atom can fluoresce. So that's just something to keep in mind. Okay? So absorption, emission of light. There's also light scattering. So some detectors are based on scattering of light, or some detection is based on scattering of light. So we're going to learn about scattering of light. And also there's diffraction of light. So diffraction is the fractionation of light into multiple waves of singular wavelengths. Okay, so these kind of interactions. And then if we look at the region, you'll see here that the light ranges from radio frequency, microwave, infrared, visible, near UV, vacuum UV, X-ray, and gamma rays. So these are the smallest. So the gamma rays is the smallest or the shortest, and this is the longest. Radio is the longest. We'll learn about frequency in a minute, but with the higher energy, or maybe let me put it the other way. The shortest variation, the shortest wavelength is associated with the highest frequency and is associated with the highest energy. And I'll show you why in a minute. As it becomes longer, it carries less energy. Okay? So it's an inversely proportional relationship between the length of the wave and the energy. The smaller the length, the highest is the energy. So things to remember. Okay. We have, based on the different waves and the different interactions and the different species, we have different types of spectroscopy. We're going to learn about UV vis absorption spectroscopy. We're going to learn about emission fluorescence. So absorption, fluorescence. In the UV vis range, we're going to learn about infrared, the infrared obviously range. And then we have unique absorption for atoms. So atomic absorption and emission. So atomic absorption and inductively coupled plasma emission. It's okay, I'll have the abbreviation in the following lectures. So you'll learn about that when we learn about measuring minerals. So we'll have a lab on atomic absorption. We won't have a lab on emission. We don't have an ICP, unfortunately, but we'll learn about the principle. We're not going to learn about nuclear magnetic resonance just because it's outside the scope of this class, but it's another powerful tool for structural elucidation. I'll mention it a little bit when we talk about mass spectrometry. Mass spectrometry is not a matter of absorption of light or electromagnetic radiation. It is basically if you notice, all of this is spectroscopy, but you don't say mass spectroscopy, you say mass spectrometry. So it's very wrong to say mass spectroscopy. So it's mass spectrometry because it's dealing of identification of ions in the presence of radio frequency and electrostatic field. So you learn about that with Gary next week. Mass spectrometry is a very powerful detection, but the commonality between the two is you get spectra. So that's why it's called spectroscopy, spectrometry. So you get a spectra. Here you get a spectra of ions. Here you get a spectra of absorption or emission. Okay. So before we head out, let's talk a little bit about application of spectroscopy and spectrometry. So can you tell me a few applications from what you heard so far from the semester, what you did in the lab so far? So applications. Don't blank out. It's just, you know this.
Quantification, like for lactose.
Quantification. Yes, we measure absorption, we measure emission, we quantitate. We get area under the curve, and we use it to quantitate. What else? I showed you in the lab, especially the HPLC lab. What did we look at from the PDA? Identification. So we use the spectra for structural identification. Perfect. So we have now quantification, we have identification. Also in the HPLC lab.
Yeah, well, I was going to say it can be
Molecular,
weight.
molecular weight or structural elucidation. Okay, so it's not just molecular weight, you can get structural elucidation. You can look at the spectra, and we will learn that with IR, for example, you get a very nice spectra. It gives you structure on a molecular level for bonds, what functional groups and how they're bonded together. With MS, you can get molecular weight. With NMR, you get complete structural elucidation of the entire molecule. So really, structural elucidation is a big thing. Identification, detection, quantification. The last one is forensics. So if you know nothing about, it's like we talked about it actually today in lab. If you don't know anything about the compound, you start simple. You look at UV detection, then you get the molecular weight, then you get NMR, and then try to determine what that compound is. Especially if you have a contamination that you're not sure what it is in food, then you start kind of a forensic approach to identify. And a lot of these forensic approaches are spectroscopy and spectrometry. So it's a very, very powerful tool in food analysis. And with this happy and high point, I'm going to send you off. Yeah, turn in your +2.